Okay, thank you. Well, it's a pleasure to be here, or let's say it would be more of a pleasure if I were there. But I appreciate the opportunity to deliver this opening talk. Thanks to Felipe and to the organizing committee for making this happen, and I'm looking forward to a terrific meeting. I'd like to talk this morning about some recent work looking at problems of complex forests and asking the question, what can we learn from artificial intelligence techniques? And there we go. So the big picture of research here, I live in the northeastern United States, and the forests that we are trying to manage are very complex structurally and compositionally. And I'll put some numbers on that for you in a minute. But our forest management is dominated by natural rather than artificial regeneration. There's almost no planting of forests in this region. Rather, we rely on natural systems to provide the new seedlings to carry forward the next generation of trees. And as we do that, we face a lot of challenges throughout my whole career. People have come up in meetings saying, "Oh, I'm worried about are we getting enough regeneration of this species or that species or some other species?" This is a chronic and widespread problem, suggesting that we're not meeting the challenges of sustaining our forests into the future in the way that we would like. Now, the challenge with that, or a challenge with that, is that obtaining tree regeneration is a complicated problem. There's a lot of factors that drive whether or not we obtain natural regeneration and what the species mix would be. Competition, climate, site quality, which has multiple dimensions to it, as well as herbivory. We have a strong deer population in our region, as well as moose in the northern portions of the region, and they certainly have an effect, as well as our own management, both our intended and unintended consequences. But, or perhaps because of that, we really don't have good quantitative models of tree regeneration. And the ones that we have are very few, they're very simplified, and they tend not to capture important dynamics. So maybe there's a role for machine learning here. We actually have quite a bit of data. Can we turn the computer loose? Can we let the computer discover patterns that would help guide our understanding and our management? That's really where we want to go today. To put a little more background on this, we've taken a look using our data from our National Forest Inventory at regional harvesting patterns. Now, this is the region that I'm going to talk about today. It's the very northeastern corner of the United States, with Maine in the upper right, New York off to the west, to the left, and the rest of New England, as we call it, sort of sandwiched in the middle. One of the things that I want you to ignore here, there looks like there's a lot of dots in Maine. That's simply because there's more inventory data from Maine. It's not because there's more timber harvesting necessarily in Maine. But one of the takeaways here, there's lots of different colors of dots. Timber harvesting practices vary widely. This is almost all private land, and harvesting is almost completely unregulated. The other thing that I will tell you about these dots is that about a third of the harvests in the region consist of either commercial clear cuts in which all the valuable trees are simply liquidated, leaving behind a residual of lower quality trees, or they're high grades, in which case it's simply preferential harvesting of the higher quality trees and the more desired species. There's a lot of work to do in this region to foster sound silviculture that will lead to sustainable forests into the future. And one consequence of that, when we simply take a look at what is the state of the forest, nearly 40% of our regional forests have impaired composition and stocking from a timber management perspective. That's leaving aside some of our other important management objectives like wildlife habitat and carbon sequestration. But when we try to model restoration pathways to get these forests back on track, that's a multi-decadal problem, and we find that the answers that we get are very sensitive to what we put into the models. What kinds of trees will be regenerating in the forest? Unfortunately, because of our lack of good quantitative models, we tend to use a very simplified plug-in approach. Nearly all of the published studies trying to address long-term management problems in this region simply put in what is guessed to be a representative or reasonable level of tree regeneration, a certain number of seedlings of a small number of species, and we hope that that's adequate. And I've been involved in enough of these studies. We pick these by looking at what other people have done, sitting at a blackboard and saying, maybe we should put in a few more of these species for our specific case. It's not very satisfying and it's not very um, robust analytically. So we'd really like to overcome this. We'd like to have a better quantitative picture of what kinds of regeneration we can expect to better inform not only our management, but our models of the future. So I said we're going to take a machine learning approach to this and let data drive some of our conclusions. These are the data we're going to use. This is the data from our National Forest Inventory System, or what we call the Forest Inventory and Analysis here in the States. And the data on regeneration come from this sort of strange cluster plot design. There's approximately a plot per 2,000 hectares of forested land. And we're talking about seedlings and saplings that are either smaller in diameter than 2.5 centimeters, or they're shorter than breast height. Most of these plots, these are permanent plots, and over the last 20-ish years, it varies by state, most of the plots have been remeasured 2 to 4 times. So strictly speaking, we have clustered data here, or longitudinal data. We have 22,000 observations in total if we consider the observation of a plot in a year as an observation. But those observations only occur on about 9,000 unique plots. So one of the questions we're going to be asking methodologically is how important is it to deal with that clustering or longitudinal nature of the data? Now, to give you a sense of complexity, our forests are not monocultures. Um, we have about 135 taxa in the overstory tree data. That's a lot. That's a lot of species. Now, maybe only a couple of dozen of those sort of dominate things numerically, but that's a lot of taxa to keep track of. And we have a similar number in the regeneration data. Again, many of those species are unusual, rare, localized, but there's quite a few taxa to keep track of if we wanted to do that. And in any given stand, we expect 6, 7, 8 uh, overstory species and a similar number in the understory. So this is not a simple problem of modeling a specific type of regeneration in a specific type of forest. Moreover, if we tried to model the regeneration of individual species, we'd find that these data are zero inflated. There's a lot of zeros. There's a lot of places where any given species we might look like is absent, and we'd find that they're clumped as well. This is a nightmare statistically, and machine learning techniques to deal with those kinds of data are still, I would say, in development. Another limitation of the data, and there are some limitations, but one that we want to be aware of, is that at very high seedling densities, the counts that are represented in the data are often essentially ocular estimates. The field crews don't sit there and count 30 individual seedlings on a very small plot. They look and they say that's about 30. So there's a lot of sources of inaccuracy, and there are certainly limitations in the predictor data that are collected. So for today's talk, I'm not going to try to model the regeneration of individual target species. That's actually a huge challenge. There's too many species, and as we've mentioned, the properties of those data actually make them difficult to model well. Rather, I'm going to focus on community level traits, and I'm going to focus on 4 traits today. The first is the simplest, of course. It's just simply the number of seedlings and saplings per hectare. I've log transformed those data to achieve some better statistical behavior. Now, there's one good piece of fortune here. there's always at least one seedling on at least one of those four little plots at every plot in the data set. So I don't have to deal with what to do with when we log transform a 0. I was very happy to find that out. So that's a good simplifier. The second attribute that I want to model is the community-weighted mean shade tolerance. We have a wide range in shade tolerance in the species mix, from aspen, which is very intolerant, to spruce and hemlock and sugar maple and beech, which are very shade tolerant. What I'm modeling here is simply the weighted average across the community assemblage in the understory. And that's using shade tolerance scores from Ninemets and Valladares. A 1 is very intolerant, a 5 is very tolerant. I'm going to model the proportion of the seedlings or saplings that are softwood species, conifers essentially. And that's a very simple proportion ranging from 0 to 1. And finally, I'm going to model the proportion that are of what we consider primary species. These are species that we've identified as having the highest financial desirability for timber management. This is an unabashedly timber-focused perspective. And to give you a sense of those primary species, out of the 130 so in the community, it's really only 10, maybe 9, because many people would consider Acer nigrum and Acer saccharum to actually be the same species. We treat them the same. They have essentially the same wood properties, the same silviculture, the same ecology. But we've got a maple, we've got a couple species of birch, one of which is intermediate tolerance, yellow birch, one of which is very intolerant, paper birch. We have black walnut, which is quite rare and very valuable. We've got a couple of conifers, red spruce and white pine, and then a few more hardwoods, black cherry, white oak, red oak. These are our primary species. These are our money species. And from a timber management perspective, we'd like to see a generous proportion of these species in the mix. The question is, can we simply predict the quality of the regeneration mix without going down to the individual species level? Now, the variables that we've pulled out to try to predict these four traits are somewhat limited. There's things I'd love to have in the data that simply aren't there. But 19 predictors is enough to need to sort through and maybe reduce. We've got 5 just general site variables, where we are in the world: latitude, longitude, elevation, slope, and aspect. We've got a relative density. For those of you who are silviculture fans, this is a modified additive version of Reinecke's stand density index that uses species traits, wood-specific gravity as a controlling factor. So we can split the relative density of the forest into total relative density, the relative density of the overstory in softwoods, and the relative density of the overstory in primary species. We can make the same split over basal area per hectare. Basal area per hectare is much more commonly used in an applied context, but we know it has limitations for describing the forest overstory ecologically. We're including it here as a comparison and to find out if the more sophisticated relative density measure actually gives any consistent advantages in prediction. Stand diameter is one of the easiest things we can pull from the overstory plot data. Almost all the time in forestry, we use quadratic mean diameter, which is the root mean square diameter of the trees, if you want to think of it that way. But there are other measures, and I've got a paper coming out that takes an analytical approach, and we realize that some of these different measures of stand diameter are actually quite different in complex stands. So in addition to quadratic mean diameter, we're looking at the top diameter, or the diameter of the thickest 100 trees per hectare, as well as the basal area weighted mean diameter, which is not very commonly used in the US, but is more commonly used in parts of Scandinavia in forest models. So we wanted to give that one a try. Stand height, Laurie's height, which is the basal area weighted mean height, as well as top height, which here is the height of the tallest 100 trees per hectare. And then a few other variables that we thought might be important. Stand age, although that's a very funny variable to measure in a complex stand. The Shannon's diversity of the species assemblage, looking at the basal area distribution. as well as whether or not there was harvest in the most recent 5-year inventory period. I had initially thought, and we will find out that it's not a terribly good predictor, that whether or not there had been recent harvest, recent understory disturbance, scarification, and so on, might be an important predictor. Well, let's see how that turns out. So the approach we're going to focus on today, I've dabbled with a few different machine learning approaches with these data. But for today, I want to focus on our familiar friends, random forest, and a less familiar version of random forest, mixed effects random forest. I mentioned that we have longitudinal data here. We have the same plots remeasured multiple times. Mixed effects random forest is a way to try to account for that clustered nature of the data in the modeling approach. We want to compare these two approaches, ask whether dealing with the complexity and the clustering is important. We're going to look at some variable selection approaches. Now, these unfortunately rely on the simple random forest, but we'll see what they tell us. And we're also going to do some evaluation using independent reserved data because we can't necessarily rely on the out-of-bag predictions from random forest. Details, we did an 80-20% calibration validation split of the data. And we did this two ways. One is treating the observations completely independently, so a completely random calibration validation split, or making the split based on unique plots, so withholding 20% of the unique plots from the training data and reserving them for strictly independent validation. So again, when I talk about this 80-20% split, we're pulling 20% of the data out and holding it completely independent of any fitting process and using it for validation after the fact. All of the work here was done with the Ranger implementation of random forest. That's a much faster implementation than the original, and using some recoding of the MixRF package as suggested by one of our other colleagues who's in the audience today, I believe. That was a really good suggestion on the part of Dr. Yang, and I followed it, added some things for diagnosis, and then looking at variable selection on the original random forest using Baruta and vsurf as two alternatives to see if they gave us similar and useful answers. So some initial results. If we just look at the log transformed regeneration abundance, it doesn't look too bad. I've seen worse results for count data modeling things. Root mean squared error on the log transformed data of a 0.879. Which isn't so bad. Pseudo R squared about 0.5. You can see that we'd love to see a nice elliptical observed versus predicted plot. Of course, we don't get that with count data. We see some horizontal lines at low density. But the variable importance scores here were actually a little surprising. I was not expecting the primary drivers of abundance to be where you are in the world, latitude and longitude. I was expecting density to be much more of an important factor because we think that tree regeneration is driven heavily by competition. Well, yeah, that's true. There is a strong spatial pattern. I don't believe the sharp horizontal line. One of the things random forest is not great at is modeling smooth gradients, and we see that here. And the pattern with quadratic mean diameter of declining regeneration abundance with declining quadratic mean diameter, on the one hand is surprising because large trees are the source of seeds for regeneration. On the other hand, a small quadratic mean diameter simply means we have small diameter trees, and that may mean that there's lots of very small trees. So no huge surprise there, but definitely some complexity that's worth tunneling in on. For shade tolerance, we see a similar sort of out of bag versus observed pattern. These patterns look the same no matter which random forest technique we throw at it. The numbers do change slightly, and we'll come to those. You can tell, it's not catching the most shade intolerant or the most shade tolerant compositions. It's just kind of, getting some variation in the middle, which I guess isn't a big surprise. Again, where you are in the world, latitude seems to matter. But here, the prediction that competition from the overstory really matters is borne out. We see relative density and basal area essentially sharing the primary driver role when we run a full model, with relative density and basal area in terms of composition trailing behind. Um, Relative density always being a little bit stronger predictor than basal area. That's a pattern that we'll see over and over. Again, a positional gradient, I don't believe that sharp line. There should be a gentle transition that has a little bit of tilt to it, but it captures an overall regional pattern that's not far off. And again, a correct partial plot with relative density, where the more relative density, the more overstory competition, the more shade tolerant the understory assemblage is likely to be. For softwood fraction, again, similar sort of thing, funny looking predicted versus observed pattern because these aren't normally distributed data. They're bounded from 0 to 1. We could tunnel in on that more. We could try even more advanced flavors of random forest. We're going to take a pragmatic approach for today and see how close to random forest does just out of the box. Again, here's a really sharp uh, breakdown on the importance scores with relative density of softwood, followed by basal area of softwood, that overstory composition now really driving the understory composition, which isn't a big surprise. A much weaker spatial pattern and a really, really strong pattern in a primary set of predictors related to overstory composition. And finally, this is the one that's a bit of a disappointment because it really matters for predicting future stand quality. We're not doing a good job of capturing the primary species fraction in the assemblage. It's driven to some degree by overstory composition, again, relative density of primary species with support from basal area of primary species. After that, just a mess of predictors and what I would consider fairly poor predictive ability. Some spatial pattern to it. Yeah, I think I understand what's driving that because I know some of these forests, but it's not a strong pattern. And the variation associated with the overstory composition is predictable, but not perhaps as strong as we might hope. Well, does variable selection help us here? I asked, what can artificial intelligence teach us? And one of the things I would like to learn is what variables are most important. We threw 19 variables at the problem. I don't think very well in 19-dimensional space. If you can, more power to you. I like to get things down to a smaller number of things to think about. Now, a challenge here is that mixed effects random forests and some of the other more advanced versions, we don't really have good studies on variable selection. And in fact, it's not clear that some of the techniques that have been proposed remain applicable. So if we still try to do this using our ordinary random forest, um, I'll say this is kind of disappointing. You know, lots of people like Baruta. It's easy, it's automatic. We've got a big enough sample size here. Everything's significant. It's the same problem that we have in linear regression. With enough samples, things that just don't matter are still significant. So Baruta says keep everything. VSurf, which is another common choice, is very conservative. For some of these variables, it only wants to keep 2. For others, a handful. The handful never makes sense to me. And the conservatism of VSurf has been noted in the literature before, even dealing with problems where we know what the driving variables are. It often doesn't include them. So to me, this is frustrating, right? If the whole point of variable selection is to help me decide, but if the whole answer depends on which technique I choose to use, that's not giving me an answer that's different. It's like the problem in cluster analysis where you try different clustering techniques until you get one that makes sense to you to start with. I don't find that terribly helpful. So I think it's more useful to try to use a little brain power. reflecting back on the importance values, reflecting back on some of the patterns, what can we do to try to reduce the number of variables, and then see how that works on that independent withheld validation data. So, good traditional tools like our correlation plot. One of the things we see, we knew that relative density in basal area, either in total of primary species or softwoods, would be fairly well correlated. Not perfectly, an R value of maybe 0.9, but enough that, it makes sense to only keep one in the model. And since relative density almost always edges basal area, in any given situation here, we'll keep the relative density variables. There's a whole cluster of variables, that sort of yellow triangle in the middle. It's basically our stand size variables. And while in the one example I put up before, quadratic mean diameter, which is our more familiar size variable, happened to be the strongest. If we're trying to capture the power of all 5 of those stand size variables, we'll find that the basal area weighted mean or the top diameter are both strong contenders, because they're actually better correlated with stand height than quadratic mean is in complex forests. So for the examples I'm going to put up here, we're just going to go with the basal area weighted mean as our measure of stand size. Finally, elevation, slope, yeah, they show up sometimes in the full models as having modest importance, but let's just simplify down. Let's make our lives easy. Let's just keep latitude and longitude to tell us where we are in the world. So that's our set of variables. Reduce it down to 6 from 19 and ask, how well do we do? Well, you can run these models, 7 ways to Sunday, and so I did. So we've got models using simple random forest without random effects, and the mixed effects random forest with random effects. We can look at how the calibration validation split was done. Was it done independently, or was it done plot-wise? And then we can compare models between the full model and the hand-picked set of variables. And if we look at the abundance chart here, we're going to see the same pattern as we do in the other 3 variables that we're trying to predict. The first surprise is that the simplest approach, random forest out of the box, no random effects, just a crude independent cal-val split, and leaving all the variables in, always gives us the best root mean squared error on the training data, almost or nearly, and the apparent best performance on the held out data. Now, that's true, but it's also kind of cheating if we're thinking about how well would we do predicting new plots, right? This is giving the algorithm access to the entire population of plots in the data set. In real life, we're going to make predictions on entirely new plots, and that makes the plot-wise cal-val split a little bit more informative. And what we see is, no matter how we model things, once we shift to either a plot-wise cal-val split or a model that includes random effects, the root mean squared error on the held out data jumps up. I think that's a more realistic assessment of the likely prediction error for future data. The other thing that's really striking is we've done pretty well with our hand-picked set of variables. There's no practical difference in prediction ability between the full set of 19 and the hand-picked set of 6. So that feels pretty good. Did we learn something from the artificial intelligence? Absolutely. We learned how to do a better job of handpicking those variables, and that's valuable knowledge. Finally, on the use of random effects, the pattern that we'll see over and over across all of these sets of predictor variables is that while it seems like the root mean square error jumps up when we use the random effects, in fact, we've consistently get a very similar root mean squared error on the training data as we do in the held out data. And what that's telling us is that with the random effects included in the model, we're getting a more accurate within sample assessment of future prediction accuracy. So that is a bonus that might offset the additional complication in fitting the data. And to me, I think that makes using the random effects worthwhile, although for these data, the effect is modest. If we were to tunnel through this table, we'd see a very similar pattern. Yeah, but the other thing that, it takes some staring and swimming of the numbers is the effects are pretty modest as well. We've got a lot of data here, so we wouldn't expect a massive difference. The data are going to constrain the algorithm almost no matter what we do. Same thing for softwood root mean squared error. Again, it looks great with the independent cal-val split, no random effects, but that's probably an illusion. It's not a big illusion. It's just an illusion. And the same thing for the primary fraction. The lowest apparent error is with no random effects, independent split, full variable set, but that's not borne out across the other models. And there's reason to believe that their assessment of the prediction error on the held out data is actually a more faithful one to what we would expect in new application. So I asked what we could learn from AI. At least for me, I learned a few things about methodology that that I expect would be robust. First of all, there's not a huge difference in the ability of random forests and mixed effects random forests to model these kinds of data. It's a huge data set. There is clustering, but it's relatively balanced. And under these conditions, the performance of random forest and mixed effects random forest are going to be pretty similar. Now, mixed effects random forest requires a lot more computation. Is it worth it? Well, maybe. I think getting that more realistic assessment of prediction errors is worth something. On the other hand, convergence criteria, other tuning of the method, we don't have a lot of really great guidance in the literature on how to make that happen the best way possible. So I like the mixed effects random forest, but we'll see. It's a slight advantage in a data set like this. Now, what mixed effects does take away is the ability to use some of the existing semi-automatic variable selection methods. I'm not sure that's a big loss, honestly, based on the fact that we don't have good theoretical basis for choosing one variable selection method over the other, and then the variable selection methods are going to give us very, very different answers. It is a research need for mixed effects random forests, and one that I would love it if somebody would say, Mark, you missed a paper, here's the answer. For these relatively low dimensional data, again, only having to sort through, 19, 20 predictor variables and reduce that down, I think we learned enough from the AI to do that job in a fairly effective way, and that's borne out by the fit statistics. In terms of ecology and management, yeah, some fairly simple variables will answer the question, and that's reassuring. Without the machine learning, without the random forests, it would not be possible to move forward with the degree of confidence in making those choices. On the other hand, all four of these variables, even though I said, oh, I'm going to simplify the problem, they all present some serious prediction challenges. Predicting softwood fraction is easiest. That's just a simple reflection of overstory composition. The abundance of regeneration and the shade tolerance of the mix, yeah, we can kind of predict those, but there's a lot that's missing. Trying to understand whether the regeneration is desirable, that remains the hardest problem, and that's not something that AI alone is going to solve for us. There's a lot of useful information that's not collected in National Forest Inventory protocols, and that's to be understood. It's not the job of a National Forest Inventory to provide a rich, deep data set for modeling. It's the job of a National Forest Inventory to do inventory, and some of the modeling just isn't part of the plan. So I am going to double back and try and do some species specific models for our most important species. That's going to require, I think, some slightly different machine learning approaches, and we'll see how that goes. So, in conclusion, using artificial intelligence in conjunction with whatever intelligence we can bring to bear, I think is the key to making most effective use of our techniques. I love things that work out of the box without thinking because my intelligence is low. But when we put those two things together, we make a lot more progress. Good data, wow, they're critically important and they're not free. So a big thanks to everybody who's responsible for collecting these huge data sets. Um, and at the same time, AI can only mine out of the data what's in the data. It's not magical. There's a lot of things about scarification, understory, competition, all sorts of factors that we know ecologically should matter for this problem that are not in the data. We're not going to be able to magically overcome those limitations with our machine learning. And finally, with machine learning, I do think that technique matters. Yes, random forests worked well on this problem out of the box, but we did see some performance gains and some knowledge gains by using slightly more complicated techniques. So acknowledgements again, thank you for inviting me. I only wish I could be there in person. It's going to be a really exciting meeting. Want to thank our National Science Foundation, the New Hampshire Agricultural Experiment Station. And with that, I will be happy to take any questions that we have time for.